When we want to consider the relationship between two numeric variables, we usually start out by drawing a scatter plot. If the scatter plot shows that there is a pattern or some meaningful signal about the relation or association between the two numeric variables, then we proceed to compute the linear correlation coefficient. If we compute the linear correlation coefficient and it passes the test of significance, where the absolute value of the sample correlation coefficient is greater than the critical value, then we can say we've established evidence of a linear relationship between those variables. But then there remains questions to answer. One of the questions that remains to answer is, how are the two numeric variables related? In other words, correlation answers the question, how strong is the relationship between two numeric variables? Whereas, on the other hand, regression answers the question, how are they related? Now, in order to give a representation of how two numeric variables are related, we usually find a line of good fit. What does this mean? A line of good fit means that the line drawn on a scatter plot to approximate the relationship between the two numeric variables appears to describe the relation between the two variables in a very meaningful fashion. That brings up next the question of what makes a line a good fit? What criterion, what basis are we using to determine if a line is a good fit for describing the relationship between two numeric variables? The most popular technique for finding that line is based on what we call residuals, which is the difference between the actual value of a measurement and the predicted value. And this is used to mix up into a process called the method of least squares. In particular, at this basic level, we are interested in when we construct or when we carry out a regression analysis, we use the popular y equals mx plus b. Your y is the observed value and the predicted value is y at. Then instead of using m, which is just an arbitrary choice of letter, we're using beta 1, and that is still the slope of what we call the regression line. And b is beta naught, which is the intercept of the regression line, or the y-intercept. So whenever we want to fit a regression line, this is what you need to know. We need to find the values of beta naught and beta 1. So we require the formula for beta 1, which always depends on the linear correlation coefficient R, and then S of Y and S of X, which are the standard deviations of Y and X respectively. Then the formula for beta naught is the average Y bar of all Y values minus the answer we got here, put here, which seems to suggest that beta 1 must be computed first before you can compute beta naught. Well, to illustrate this, let's take an example. So, in this example, a data set is given in columns N and 0 and O of chapter 4 data sets. So let's see that data set. This is the columns N and O of the chapter 4 data sets, and I have copied it into StatCrunch. So here it is in StatCrunch. This is the data, 1, 2. So let's see, let me scroll to the right and let me scroll up. And I believe that should be here. So here is the data set right here, adjusted. And what would we like to do? We would like to draw a scatter diagram first and to comment on the type of relation that exists between X and Y. So I'll go into StatCrunch and I would like to I'm going to change the name of this to x underscore, let me say x underscore 1, or I might even just call it x1. And for the next one, I'll call it y1 to distinguish it from this x and y. That way I'm not confused. So in this case, I would like to graph the scatter plot, and I'll select my x variable. That is this one, and my y variable is this one, and I would like to compute. So I see that there is an evidence of an approximate linear relationship between my x and my y. Just to emphasize, I can see that there is a sloping downward from left to right, and that a line can best approximate this. So I would say that there appears to be a linear negative relationship. So that is what I have here in question A. Then in question B, I have been given x bar, I've been given the standard deviation for values of x, I've been given y bar, the average of all y values, and I've been given sy, which is the standard deviation for all y values. I've been given r, the sample correlation coefficient, and I'd like to determine the least squares regression line. To do that, I'll remember that this is the true nature of the least squares regression line. So I'm going to write that first. So this is the goal. I'm going to split this into two. My goal is to get the least squares regression line that will ultimately look like this, the predicted value. This is the predicted value. It is going to be beta 1 x plus beta naught. And as you can observe, that matches what we have earlier. And in particular, I need to use the formula for beta 1. So beta 1 estimated is r times the answer you get from dividing standard deviation of x divided by standard deviation of y. I believe so, which is what we had earlier, right here. So I'll compute that first. So this will be equal to my r, that is equal to negative 0.9410 multiplied by s of y, which is 1.6729 divided by s of x, which is 2.0412, and my answer will be negative, okay, let's take that away, negative 0.771 to 3 decimal places. And then, now that I have my beta 1, take note, this answer is going to be slotted back right here. But before we do that, we need to compute beta naught. What is the formula for beta naught? Well, looking back at our notes, we have that formula right here. It is y bar minus beta 1, y bar minus beta 1 times x bar. In other words, the average of all y values, that is 3.7333, minus beta 1, which is negative 0.771, multiplied by x bar. X bar was 3.8333. So that would be 3.7333. Negative times negative becomes positive, added to the product of these two numbers, which is 2.9554743, and added together we have 6.689 to 3 decimal places. So my final answer will be the estimated regression line is equal to, what is the answer for beta 1? That was negative 0.771. Then put the x beside it plus beta naught, which is 6.689. This is the regression line. Before we complete question C, there's something interesting I'd like to show you. This computation could actually be done in StatCrunch. And let's see how we can do that. We go to StatCrunch. Step 1, you go to Stats. I would like to do regression, a simple linear regression, and then choose your x variable. That'll be my x1 in this case, and my y variable is my y1 in this case. Then be sure to show a graph. So graphs with fitted what? With fitted line plots. That'll be great. And I would compute. And you will see that we have right here that same equation here. It's just that you have negative 0.7712 taken to 4 decimal place, x1, before the plus 6.6896. So there you have the least squares regression line. Then if you come down here, you see that there is another window here. So if I click on this, it takes me to the other results, page 2 of 2. And we could have known that because this says this is output 1 of 2, and I can go to output 2 of 2. This shows the fitted line, which is what the question is requesting in question C. We are to graph the least squares regression line on the scatter diagram drawn in part A. So going back here, we have what? The regression line on the scattered plot right here. So we're good to check which of these matches the options that we have here. And of course, looking at the second option, that looks like the best fit because I can see the line passes through these 2 points, and it also does here too. In contrast to the contending one, here the line does not pass through the 2 points, so I can tell that my correct answer is the second option here. With that done, we proceed to the next example. In this example, we are told that the least squares regression equation is y at equals 7.16x plus 14,478, where y is the median income and x is the percentage of 25 years and older with at least a bachelor's degree in the region. The scatter plot indicates a linear relation between the two variables with a correlation coefficient of 0.7454. We would like to complete the questions below. For part A, we are to predict the median income of a region in which 25% of adults 25 years and older have at least a bachelor's degree. In this example, what we want to show you is that this regression line, y at equals 7.169x plus 14,478, is also called a prediction equation. That is, it is an equation that if we plug in the appropriate value of x, we can get the corresponding predicted value of y. So let's do that. In this case, you have 716.9 times x. X in this case is the percentage of 25 years and older with at least a bachelor's degree in the region. In question A, that percentage is given as 25%. So in this case, take note, this axis was measured in percentage, so I can simply plug in 25 here plus 14478. And I need to get the predicted median income for that percentage. That is equal to 32,400.50. This is the median income. Question B. In a particular region, 28.3% of adults 25 years and older have at least a bachelor's degree. The median income in this region is $31,394. Is this income higher than what you would expect? Why? To answer this question, the first step, step 1, would be to compute what you would expect in this particular region that has 28.3% using the prediction equation. So y at equals 7.16.9x plus 14478. My x is this 28.3%. So I'm going to replace that with 28.3. Let me write this out in full. Let me do this. 28.3 plus that value. So what would this be equal to? That is equal to $34,766.27. This is what we would expect normally in that region. But we're told that the median income in this region is actually this value. So is this value, is it higher than this expected value? Well, the answer here is no. The income is not, this income is not higher than what we would expect in this region. And that is because the expected income is $34,766.27. Then the next step is to interpret the slope of the regression line. To interpret the slope, the first thing you should do is to look at the number beside x in the regression line. What is the sign? It is a positive number. If it's a positive number, it means that as percentage of bachelors increases, median income is also expected to also what? Increase. So, to interpret the slope now, we can say that for every percent increase in adults having at least a bachelor's degree, we expect the median income to also increase by a certain amount. And that amount on average is the value of the slope, which is $716.90. So, with that done, we proceed to question D. In this question, we are told to explain why it does not make sense to interpret the y-intercept. In order to explain the answer to this question, I'd like you to take you back to the regression line. Note that if I set x to be equal to 0, so 0 times 716.9, all of this goes to 0. 0 plus this value, I would have exactly the intercept left when x is set to 0. But wait for a second. Can x actually be 0? What is our x here? X is the percentage of bachelors, the percentage of those who have of 25 years and older, who have at least a bachelor's degree in the region. Well, that cannot be 0. I mean, in a whole region, you cannot have everybody be having no bachelor's degree. Well, that means that if x cannot be 0, the result we're getting is based on something that cannot happen. So, in that sense, it does not make sense to interpret the y-intercept because it represents the value of y when x is equal to 0. And as we have just argued, x cannot be 0 in the context of this problem. Thus, because an x value of 0 is outside the scope of the model, this y-intercept 2, which is a derivative of that assumption, has no real meaning, and we should not make any attempt to interpret the y-intercept in this context. To give an exception, note, if x can be 0 in the context of the problem, and it lies within the range of values of x used to compute the regression line, yes, we can set x to 0 and interpret the y-intercept in that scenario. Please note the difference. Having completed that question, we proceed to the next example. In this example, we are told that the data in columns K and L of the Chapter 4 data sets represent commute time in minutes and scores on a well-being survey. Complete the questions below. First, we are to find the least squares regression line, treating commute time x as the explanatory variable and the index score y as the response variable. So let's look at the data set in columns K and L of chapter 4 data sets. So here we have on your screen the data set for the commute time and the well-being index score. I have copied that over into StatCrunch, where we're going to do our analysis. So commute time and well-being index score. And what would I like to do, according to the question, to find the least squares regression line, where commute time is my x variable. So let's do that. So I'm going to go to Stats, go to Regression. I'd like to do a simple linear regression analysis. Click on that. My x variable will be the commute time, and my y variable will be the well-being index score. And I would also like to see a fitted line plot for the graphs, and I'd like to compute that. So first of all, what I have is my regression line, which is highlighted on your screen. So I'm going to take that back to my working board. And then on the next page of the output, I have the scatter plot with the fitted regression line. And you will observe that if I hover the mouse over the line, it will output or show me the regression line equation. So I'm going to copy that. So with that said, let's go back. This would mean that my index score, which is y, index score estimated, will be equal to 69.020743 minus 0.0566003708 multiplied by x, which is the commute time. Well, I can take this perhaps to say about 4 or 3 decimal places. In MyStatLab, for the most part, it requires you to take it to 3 decimal places. So I'm going to do the same. So this will become 0.21, and this will become 0.056 times the commute time. So I have that value multiplied by the commute time, so times the commute time. And then next, I would like to interpret the slope and the y-intercept if it is appropriate. First, let's start off with interpreting the slope. To interpret the slope, first I will look at the slope. It's a negative value, and since it's a negative value, it means that every time the commute time increases by 1 value or 1 unit, the index score would decrease. It will go in the opposite direction. It will decrease on average by this much. That is the value of the slope, 0.05. So this can be put in a neat way by saying for every unit increase in commute time, we expect on average the index score to fall by 0.056 on average. Then we proceed to question C, which is to interpret the y-intercept. So the first thing we ask is, can the commute time be equal to 0? Well, that is possible. So for the commute time to be equal to 0, so when commute time equal to 0, the index score, the predicted index score, which is why we have that at. This at indicates that it's a predicted value, not the actual value, is equal to 69.021. The main question we should ask here is, can we actually say that the commute time, in this case, can it be 0? What about those who work from home? Well, this makes sense. And so, for commute time of 0 minutes, the index score is predicted to be 69.021. Then next, for question D, we would like to predict the well-being index score for a person whose commute time is 30 minutes. Time to use the prediction equation. Index score predicted will be 69.021 minus 0.056 multiplied by commute time of 30. And that will be equal to 67.341. So that is the value we have there. And we can round that off to 67.3 if we want to take it to one decimal place. Now the next question is, suppose Barbara has a 15-minute commute and scores 67.4 on the survey. Is Barbara well off than the typical individual who has a 15-minute commute? The first step here is to look at the index score for a typical individual who has a 15-minute commute. We can use the prediction equation or the regression line to make a prediction of what the index score for a typical person who has a 15-minute commute should look like. So, in this case, what we will get is 68.181. Well, so this is what should be typical of any person who has a 15-minute commute. But then we need to compare this with the individual value observed for Barbara. Barbara has 67.4, which is lesser than 68.181. So this follows that since Barbara's score is less than the typical score, we cannot say that Barbara is well off. So the appropriate answer is to say that to this question, is she well off? No. Barbara is less well off because the typical individual who has a 15-minute commute score should be 68.2, rounded off to one decimal place.